Gene cloning tools, Lambda phage vectors. So let us look at the learning outcomes of this session. The Lambda DNA being 49 kb can accommodate only up to 3 kb more of DNA, and so the insert size would be around 3 kb. Therefore, this aspect has to be considered while constructing the Lambda phage. For if the size of the insert is only 3 kb, then the lambda phage is not an attractive cloning vector. And basically the 3 kb is because it can accommodate up to 52 kb of insert size in the capsid that is formed for the lambda phage. The genome being large, there are more than one cloning site, say for a single RE. And if that is the case, then it will lead to the DNA getting converted into smaller fragments, which can rearrange, but then due to rearrangement, there may be a regulation amiss. That means you can have the gene clusters getting deregulated, and therefore it will not work as efficiently as it should. The modifications have enabled inserting DNA ranging from 5 kb to 25 kb. So you can see that from 3 kb you can go till a stage where you can accommodate 25 kb of DNA, and that is because of needed modifications. The lambda phage vectors are either insertional vectors or they are replacement vectors. Many vectors have evolved with beneficial specifications. Now let us consider the normal lambda genome. So a normal lambda genome has its DNA around 49 kb, and this 49 kb of DNA is well packaged into the head of the phage. Suppose you have a gene inserted in this DNA, then obviously the size of the genome is going to increase from 49 kb onwards. And so if you have the genome becoming greater than 52 kb, then this genome with the new DNA, which is say greater than 3 kb, will not be packaged into the head of the bacteriophage. So this is something that is very clear, and this is actually trying to say a very, or trying to give a very clear message that 49 plus 3 kb is equal to 52 kb. So a 52 kb DNA can be packaged, but not more than that. So there is a limited size of insert possible, and that limited size in a normal lambda genome is just 3 kb. So if you have to use the lambda phage as a cloning vector, something needs to be done about this limitation, that it can accommodate only up to about 3 kb of DNA. So the gene insert size while using a normal lambda genome is only 3 kb, which does not make the lambda DNA or the lambda phage a attractive or a useful vector. So therefore, some modifications have to be carried out in order to increase the size of insert that is possible. Another issue that has been observed with the lambda phage DNA is that, say for example, the lambda phage DNA has been observed to have five restriction sites for EcoR1, which means that if one wants to insert a gene using EcoR1, then what is going to happen is that the lambda DNA is not going to get cleaved into two fragments, but it will be cleaved into several smaller fragments. Now, this can definitely be religated, but when they religate, what can happen is that the gene clusters that were present originally may not be the same after religation. So you may have 4 over here, 3 over here, 2 over here. If that is the case, then a set of genes that is regulated will lose its regulation because of the rearrangement of the clusters, because of the rearrangement of the genes happening due to religation. And hence, this aspect of having more than one restriction site in the lambda DNA is not a good prospect for a cloning vector. Therefore, one would have to ensure that you have minimum or only a single restriction site for a single restriction endonuclease. So that is something that needs to be modified again. So now if you consider the 49 kb lambda DNA, then one is very clear about the fact that a cluster of genes is going to help in particular function. So here one has a cluster of genes that is helping in forming the capsid component of the lambda phage and also in packaging of the DNA into the capsid component. Then you have genes present which are responsible for lysogeny. You have genes responsible for replication. You have genes responsible for lysis, that is the lytic cycle. What is very clearly observed is that between this and this, there are genes which are not required for multiplication. So you have genes over here which is required for integrating into the host genome. So for recombinant DNA technology, if you want to use lambda phage as vectors, then the lysogenic component is not really a requirement. So any manipulation that can be done between this to this, which is about 15 kb size, that is from 20 kb to 35 kb, is a set of genes that can be removed from the lambda DNA, and the lambda DNA is capable of multiplying and getting into a host, and therefore you would have multiple number of the gene of your interest possible. So you will only find that these lambda phage vectors where this component, this entire stretch of DNA, if it is removed, then or it is replaced, then the lambda phage vector will go directly into the lytic phase. It will never go into the lysogenic phase. So basically, this major portion of the area that can be deleted would lead to a non-lysogenic lambda phage, which is absolutely okay if you have to use the lambda phage as a cloning vector, because what is needed in a cloning vector is that it multiply and amplify the gene of interest. And if the lambda phage goes into the lytic cycle, then obviously the amplification is going to be greater. If it goes into the lysogenic phase, then it becomes dormant and therefore does not multiply. And so the gene of interest also does not get multiplied. So strategically, by removing or by deleting this part of the lambda DNA, one is making space for the insert. So if you remove 15 kb, then 49 minus 15, okay, would give you about 36 kb. And so you can insert a DNA of 15 kb to bring it back to 49 kb or to 52 kb. So about 15 to 18 kb of gene size, gene insert uh, can be cloned in lambda vector. So that is something that is possible, and therefore this is the region where maximum manipulations have been carried out. The second issue where we talked about the fact that you have several eco R1 sites. This is an example. You could have similarly for different restriction endonucleases. But say for example for eco R1 you have 5 eco R1 sites, and essentially you need only one eco R1 site. So therefore what will have to be done is that the restriction site, which is GAATTC for eco R1, will have to be modified at 4 sites except one. So it will leave one eco R1 site, but all the other 4 will be modified, and so eco R1 will not be able to cut at that point. So if the GAATTC is converted to GGATTC, then this GGATTC will not be recognized by eco R1 and the DNA will not get cut. So this is possible by in vitro mutagenesis. Through mutation, one can replace the A with G, and the moment it gets replaced with G, you now have a restriction site which cannot be cleaved by the respective restriction endonuclease. So this is one way of ensuring that you're removing the extra restriction sites. The other way is to carry out normal selection of those mutants of phage which do not have 5 restriction sites but has eventually only 1 restriction site. So what is generally done to create such mutants is that the lambda phage is inoculated in a culture which has E. coli that produces EcoR1. So if you have E. coli that can produce EcoR1, EcoR1 will immediately go and cleave the lambda DNA, and so the phages will not grow or the phages will die because the entire DNA is cleaved. Suppose out of the many phages, one of the phage is such that is a mutant, and the mutant is such that it has less number of EcoR1 sites, then there is a possibility that those lambda phage will grow in the E. coli. And so you will see a plaque formed. Now this plaque formed, say for example, has instead of 5 restriction sites only 3. That means naturally mutation has occurred, or naturally the phage that is growing over here has adapted to the presence of EcoR1 in the E. coli. If you take this phage and grow it again in a media which contains E. coli that is able to produce EcoR1, the phage will adapt further to to kind of grow in a situation where EcoR1 is produced. Then it may be possible that you have eventually the phage adapting such a way that it only has or it has no EcoR1 as well. That is also possible. So adaptation by the lambda phages to survive the EcoR1 produced by the bacteria is the key to natural selection. Now, let us look at how or what are lambda insertion vectors. So we know that lambda phage vectors can either be insertional vectors or replacement vectors. So insertional vectors means that we know that from 20 kb to 35 kb is the non-essential region when you use the normal DNA, lambda DNA as a vector. So you can actually insert a DNA within this region and the lambda phage will continue to work normally. So you can cleave out this region, completely remove this region, and uh, then what happens is that from 49 kb it becomes 35 to 40 kb, and then within that you can have your gene of interest being inserted. So for example, lambda GT10 is an insertion vector where within this non-essential region which has a gene CI, and this CI is a gene that is necessary for integration. So within the CI there is an EcoR1 site. So if one is able to cut this at this point, then the CI gene gets disrupted. So you have what is called as insertional inactivation of CI. And when you have insertion inactivation of CI, the lambda will not get integrated into the host genome. So therefore, you will find that it leads to non-lysogeny, which is fine. So if such a case happens, then you can have about 8 to 10 kb of gene of interest being inserted in the lambda DNA. When you have such a situation, what you will get is that you would have in a plate containing E. coli and E. coli, you will find that certain uh, plaques that are formed. Okay, now what is plaque? So we all know that when lambda phage infects E. coli, ultimately the E. coli is going to get lysed and you will have the lambda phage being released. Those lambda phages will infect the neighboring E. coli. Those E. coli will get lysed and you would have the phage released. So therefore, with every infection cycle, you will find that the E. coli is getting lysed more and more. So as you have more and more E. coli getting lysed, you will find that at certain regions you have no E. coli growing. And so those regions are called as plaques. And if you find those plaques, then it means that those E. coli have been infected by a lambda phage and the E. coli has got lysed. So where other regions you have lawn-like growth of E. coli, in the regions where the lambda phage has infected the E. coli, you would have a clear zone. So wherever you have clear plaques, okay, then that is considered to be recombinant. Why is it considered to be recombinant? Because the lambda phage in the lambda GT10 has an insert in the CI gene. CI gene is a gene that is required for integration, but because you have an insert within the CI gene will get inactive, and because this gets inactive, the lambda phage will not go into lysogeny, instead it will go into lytic cycle. So therefore, you will have more and more E. coli getting lysed, and therefore you will have clear plaques being formed. In non-recombinants, because the CI gene is not disrupted or there is no insertional inactivation in CI gene, the lambda phage will become lysogenic, and so when it becomes lysogenic, the number of E. coli that is going to be lysed is very, very less, and hence you will find turbid plaques being present. So effectively what we are understanding is that if you have clear plaques, it is indicating that it is a recombinant. If you have turbid plaques, then it is indicating that it is a non-recombinant. Another example of insertion vector is lambda ZAP2. In lambda ZAP2, uh, here what you observed is that within the CI gene you had the EcoR1. Here what you have is that within this non-essential region, one is inserting. So the modification has been made in such a way that a lag Z prime is inserted as a selectable marker, and this lag Z prime within it has a polylinker which is a multiple cloning site. So whereas here you could only cleave with EcoR1, here what you have is that you can use several restriction endonucleases to cut and insert the DNA of your choice. Which means, therefore, what we understand is that at this point, therefore, you would again have an insert happening. When you have an insert happening, the lag Z prime will get inactive. So this is what is insertional inactivation. And we all know that when you have the lag Z prime inactive, you would get white colonies. So the lag Z prime not being active, beta galactosidase is not formed, and beta galactosidase cannot convert X-gal into a blue colored product. But if there is no insert, okay, the lag Z prime will be active, it will produce beta galactosidase, and it will convert X-gal into blue colonies. So this selection is lag Z selection system because you have the selectable marker as lag Z prime. Therefore, here very clear that is observed is if you have a clear plaque, okay, that is very clear and white plaques, it is recombinant. Whereas if you have non-recombinants, obviously the lag Z prime being active, it will convert X-gal into a blue colored component, and so you will get blue colonies. So this is blue-white screening, and this is simple screening with respect to the fact that you would have the lambda phage lytic or the lambda phage non-lytic. So that is how lambda phage vectors have been used, and you can see how instead of just a 3 kb insert, because of the specific deletions in the non-essential region, you can now insert a DNA of about 8 to 10 kb. If size of the DNA with the insert is greater than 37 kb and less than 52 kb, only then it can be packaged. So if the DNA is anywhere between 37 to 52 kb, it can be packaged. If it is less than 37 kb, it cannot be packaged. And if it is greater than 52 kb, it cannot be packaged. Now, this is an important factor because size itself can be a mode of knowing whether it is a recombinant or whether it is not a recombinant. Now we come to another way by which the lambda phage vectors are used, and that is replacement vectors. So if you can see over here, again in the non-essential region, what has been inserted is a stuffer fragment. A stuffer fragment is any DNA which is just present within the non-essential region. Okay, this is cut and removed, and in place of the stuffer fragment, a gene of interest can be inserted. So you basically have replacing a stuffer fragment with a new DNA. Now, the stuffer fragment itself can have several restriction endonucleases, and therefore it can be cut into several smaller fragments so that it does not reinsert itself in the lambda DNA. So that is another thing that can be ensured. So what you are ensuring therefore is what ligates is only the new DNA, or what could happen is that you have this being self ligated, and if this becomes self ligated, then its size will be less than 37 kb, but with the new DNA, its size would be within 52 kb. So if this is now within 52 kb, this will get packaged into the capsid or the head of the lambda phage. But if you have the stuffer fragment removed, but no DNA getting inserted, and if then the size is less than 37 kb, this is not going to get inserted or packaged into the coat. So the example for this is lambda EMBL4. In lambda EMBL4, you have these two regions which have three restriction sites. One is for EcoR1, one is for BAMH1, and one is for SAL1. And you have the same three S, that is SAL1, BAMH1, and the EcoR1. So depending on if you're using SAL1, it will cut at this point. Okay, so it will remove this part. If you use BAMH1, again it will cut and it will remove this. So you can use either of the three restriction endonucleases to remove the stuffer fragment. So this is a stuffer fragment. And using the same sticky ends, you can have the new DNA inserted, and it can be anywhere up to 23 kb. So you can see that how in insertion vectors where you could insert up to 10 kb, but with replacement vector you can insert up to 23 kb. So therefore you can see how from 3 kb in a normal DNA, by modification now you are enabling insertion of 23 kb gene size into the lambda phage vector, and therefore lambda phage vectors today are a very popular and very commonly used cloning vector. So recombinant selection is based on size over here as mentioned. Now lambda phage vectors can be used as a circular lambda DNA, or it can be used as linear DNA as well. So when you have the circular DNA, the lambda DNA present as circular DNA, because we know that the COS sites are basically sticky ends. So they are 12 nucleotide long sticky ends. So two COS sites will come together to anneal, and then you have this circular DNA being formed. Here you have an EcoR1 site, say for example, then any DNA which has sticky ends of EcoR1 can get inserted over here when cut with EcoR1. So now you have the circular DNA with the new DNA present in the lambda phage DNA, and this can be then transfected into E. coli. So this becomes the recombinant molecule. You can also use the lambda phage as linear DNA. So you can see that linear DNA means this is one COS site and this is the second COS site. Oh, sorry, this is one COS site and this is the second COS site. But if EcoR1 is present, then the EcoR1 will cut it in such a way that these will be sticky ends for the EcoR1. So when you mix these fragments of lambda DNA with sticky ends of EcoR1, when you mix them with new DNA that has sticky ends of EcoR1, then you can see that these sticky ends will anneal to the restriction to the EcoR1 sticky ends and form a kind of catenated DNA. So you will have the new DNA inserted within two COS sites, and we all know that any amount of DNA that is present within two COS sites can get packaged into the head of a lambda phage. So that is how every catenated DNA containing the new DNA can get inserted into the lambda phage. So that is also the way it can be used. So you can get catenated DNA just like you get with rolling circle replication. Now, lambda phage vectors have also been used as a hybrid with plasmid. So what you can see over here is a typical cosmid. Cosmid is basically when you have a lambda DNA fragment containing the cos site hybridized to a plasmid. So you can see how You have PUC8, okay, which contains ampicillin resistant or PBR322 as well, with an ampicillin resistant gene and its origin fused with the lambda DNA that contains the COS site. And this has, say, for example, the BAM-H1 restriction site. So, using BAM-H1, okay, you can get linearized, PJB8. This is the cosmid, okay. So you can see how the linearized, this thing has two sticky ends of BAM-H1 with the ampicillin resistant gene and the COS. Now, if you use BAM-H1 cut new DNA, these will bind to the sticky ends of the BAM-H1, and you can see that these DNA are connected to each other by the new DNA. But interestingly, what happens is that you have COS site of this one and the COS site of the next catenated DNA. So anything that is there between the two COS sites get packaged. So therefore, you will always find that this new DNA will be present in the recombinant cosmid DNA. And with cosmid, what has been observed is, because you're not using the full lambda DNA, using the plasmid, the insert size can be greater than 23 kb. So such lambda DNA are used to clone big genes or large DNA molecules. Now, because you have this several lambda genes lacking, okay, no plaques are formed, but you grow them on ampicillin containing media, and the colonies that grow on ampicillin containing media are the recombinants. Okay, so that is something there. So it is using two facts. One, the size. Okay, the insert ensures that the size of the lambda DNA is such that it is packaged into the into the phage, and the ampicillin resistance is a resistant gene is allowing only those E. coli to grow which have this ampicillin resistant gene, but that E. coli has the phage particle within it. Okay, so therefore this is how the selection of recombinant PJB8 molecules are done. So they are selected on selective media, just like a plasmid based recombinant is selected. And the recombinant selection also can be done according to size. So it is using both the ampicillin resistant gene and the size of the entire lambda DNA between one COS site to the other COS site. So let us make the conclusions. Lambda DNA can have select regions deleted to accommodate a gene of interest between 5 to 25 kb. The lambda DNA has also been modified such that multiple cloning sites are not present. These multiple cloning sites are for one restriction site only. Moreover, selectable markers have been introduced for recombinant selection. The vectors are either insertion vectors or replacement vectors, with the latter, that is the replacement vectors, being able to accommodate an insert size of up to 20 kb. Hybrids of plasmid and lambda DNA have enabled ease of recombinant selection as well as accommodating a larger insert size. Therefore, despite lambda DNA being large in size, it itself being large in size, it has been modified to make its use as a cloning vector with ease of selection and transformation efficiency. The ability to clone a large DNA is definitely an advantage, and that is why lambda phages or lambda vectors a, uh, are a type of vector that has been commonly used for cloning experiments. Thank you.